two-stroke engine. Small, insignificant. Even considered expendable by some of its users. To others, it gives a happy superiority. In many ways of travel, the two-stroke engine has created a minor revolution. Through its modern efficiency and cheapness, it has brought a way of getting about to people who otherwise couldn't afford it. It has been the stimulus to revolutionary designs. And even ordinary motorcycles are being thought out afresh. The habits of millions of people throughout the world have been changed by the two-stroke engine. It has not only satisfied needs, it has in turn created new kinds of activity, bringing people together across a country, or even rallying them across a continent. But the two-stroke engine is not always small. This family car is a two-stroke. These trucks are two-stroke. This sports car is a two-stroke. This railway engine is a two-stroke. These two-stroke scooters are entering a two-stroke ship. Most large motor ships are two-strokes, for a two-stroke engine is lighter than a four-stroke of the same power. And in a ship, every bit of weight and space counts. How does a two-stroke manage it? This is a typical four-stroke single-cylinder petrol engine. The two-stroke is basically similar, but can operate without the valves, springs, rockers, push rods, timing gears, camshafts, and so on. So much weight and complication lost for the start. Then how does it work? Let's go back to the fundamental cycle of the internal combustion engine. Whether this is petrol or diesel, four-stroke or two-stroke, its first need is a cylinder full of air, mixed at some moment with fuel in the form of droplets. The piston is made to rise, compressing this gas charge. Now, either by a spark or by the heat of compression, the mixture of fuel and air is ignited. It burns and expands explosively, giving power by pushing the piston down to the bottom of the cylinder. The spent mixture is no more use. The problem is how to get rid of it and get fresh mixture in so that we can repeat the cycle as often as we like. How do we get from this red spent gas to the fresh blue gas? In the four-stroke engine, the piston goes up again. It pushes the spent gas out through the exhaust valve, and as it starts to come down, it sucks in fresh mixture through the inlet valve. So we change our red spent gas for new blue. But notice that we take 2 more strokes of the piston to do it. In fact, out of 4 strokes, Only one is productive of power. In the two-stroke engine, instead of power every 4 strokes, we get power every 2. The compression stroke is the same. The ignition is the same. The explosion and power are the same. But now, the piston first uncovers an exhaust port, a hole in the side of the cylinder, and then an inlet port, a hole on the other side. Through this, the incoming mixture under pressure acts like a piston and pushes the exhaust gas out. This is the situation halfway. In reality, it's continuous and very quick. So we change our red spent exhaust gas for fresh blue gas, without extra strokes of the piston, getting a power stroke 1 in every 2, and in theory, twice the power for a given cylinder volume. This diagram is an idealized picture of what happened in older type engines, when the incoming gas was pushed up and across the cylinder by a deflector crown on the top of the piston. Today, greater efficiency is obtained through more complex gas flows, but with a simple piston. The necessary direction and speed is given to the gases through the careful shaping of the ports. The size and angle of opening of these ports are vital and are fixed carefully by the manufacturer. Don't imagine you can easily improve on them. Remember, anything you file off, you can't put back, and you will almost certainly have made it worse. Why? Look again at the slice through a typical modern petrol two-stroke. No valves, but instead several large holes, the ports, which point in different directions. Remember, we need mixture under pressure to flow into the top part of the cylinder. This pressure is created in the crankcase. The underside of the piston acts like a pump as it descends into the sealed volume of the crankcase, here cut away, but where the free space is made as small as possible. Mixture in the crankcase will thus be compressed. Our next job will be to get it into the top. But notice that as the crankcase is now a compression chamber, it can't be used as a sump for lubricating oil. We'll see in a moment how everything gets lubricated. First, let's see how the mixture of petrol and air gets into the crankcase. When the piston rises, it creates a partial vacuum there, so that when the skirt of the piston uncovers the inlet port, mixture from the carburetor is sucked under the piston into the crankcase. As the piston descends, it closes the port. If we have added a little lubricating oil to the petrol, making petroil, the vapor in this mixture will consist of petrol and oil droplets, in reality in very fast motion. The oil gets deposited on the cylinder walls and on the moving parts. The piston descends further and compresses the mixture. Stop and look at the cylinder the other way. When the piston continues its downstroke, the mixture under pressure flows up through the ports, which are uncovered by the top of the piston. This is called transfer. At the end of transfer, the cylinder is full of fresh mixture, ready to begin its cycle. To see this, go back to the first view. The piston continues its upward stroke and compresses the mixture in the cylinder. At the same time, it draws more fresh mixture into the crankcase. Near the top of its stroke, there is the spark, explosive burning of the mixture, followed by power. Towards the bottom of the power stroke, we have to get rid of the red spent gas through the exhaust port. Partly, it goes out through its own expansion, the blowdown. But look at the other aspect to see how the incoming fresh gas completes the process. As the piston uncovers the transfer ports, This fresh mixture, under pressure in the crankcase, flows out into the cylinder itself, pushing the spent gas before it. This is called scavenging. Scavenging should be completed just as the piston closes the port again. All the red exhaust gas is out and replaced by fresh mixture. The cycle is complete and ready to go again. To see it fully, let's look at both aspects at once. First, compression in the top part of the cylinder, at the same time as the sucking in or induction of the fresh mixture below. Ignition, followed by power, at the same time pre-compression in the crankcase. Blowdown of the spent mixture from the top, and the start of transfer of fresh mixture from the crankcase. The transfer, called scavenging, because it chases out the old gas. Scavenging is the heart of the process, and the gas flows are three-dimensional and complex. The aim of the scavenge is to conduct a pincer movement round the spent gas. This is what we hope will always happen. A cylinder full of spent gas going out, and exactly a cylinder full of fresh gas coming in. In practice, scavenging isn't 100%, and some fuel is wasted. Some exhaust gas also gets left behind, especially when the engine is turning over slowly. And the explosions become intermittent, a tendency of many two-strokes when idling. This fault is now being overcome by improved design. A light hand on the throttle is best if you want to economize. If, for example, you open up fully to keep the same speed in top uphill, the fresh mixture tends to overshoot. That is, go out of the exhaust port without being burned, and so be wasted. Full throttle doesn't pay. Though it doesn't matter on this two-stroke, a diesel two-stroke. For in a diesel, the fresh gas is pure air, and if some goes straight out of the exhaust, it doesn't cost much. Here is the starting charge of pure air in the diesel. This is compressed by the piston, but much more than in the petrol engine, so that it gets very hot, and now, when fuel is injected, it burns explosively at once, giving us the power stroke in a similar way to the petrol engine. Fresh air, compression, injection of fuel, explosion, power. Again, the problem is how to get rid of this spent gas and replace it with fresh air. Again, it can be done with 4 strokes or with 2. In the 2-stroke diesel, we need first a supply of fresh air under pressure at the inlet port, and then an exhaust port. Now the fresh air can enter and scavenge the cylinder as before. And it's a good thing if the fresh air overshoots a little, for it ensures that all the spent gas is out and nothing's wasted because it's only air. But it does mean that we need a higher scavenge pressure than can be got from using the underside of the piston in the crankcase as a pump. So in diesels, the crankcase is free for normal lubrication. And right outside the engine, a separate rotary pump or blower is used to compress the air. This is driven by the engine. This cross-scavenging is used in a number of diesel engines, both automotive and marine. It is basically the simplest method of scavenging, but to make it successful in practice, each port must be divided up into a number of small ports, carefully shaped and directed to produce the combined stream of gas. Years of experience and experiment have gone into getting the curves of the ports of this marine engine cylinder the shape they are now. And experiments still go on. Here, test work is being done with a model cylinder to find out the efficiency of scavenging using different port designs. Inlet and exhaust ports are arranged in a metal ring, and to the ring is fitted a glass cylinder. The port ring is now hidden in the structure. Instead of gases, which are difficult to analyze, liquids, which behave similarly, are being used. The red-colored one represents the spent gas. Waiting to enter is blue liquid to represent the scavenging air. At the given moment, the inlet and exhaust ports will be rapidly opened and shut by the hidden piston. In practice, scavenging is too fast for the eye to analyze, and high-speed cinematography is used. The apparatus is ready. The camera is up to speed. Okay, shoot. The blue liquid rushes in and scavenges the red. See what the high-speed camera shows. The cylinder at the start. Shoot. Not a good scavenge. The action is slow, and it appears more a mixing than a scavenge. Look at it again. Now, the apparatus has been refitted with another design of port rings and is ready for test. Shoot. A great improvement. See it again. The incoming gas curls neatly round and drives out the old. Simpler and more efficient gas flows are obtained with end-to-end scavenging, though the engine itself is more complicated. The old exhaust duct goes and becomes part of the inlet system, which, to see properly, we'll take away the piston. The incoming gas can now enter through the inlet ring, a series of holes all round the cylinder. To control the exhaust, a valve is introduced in the head of the cylinder. Fundamentally, the cycle is similar to the other engines. But now, towards the end of the power stroke, the exhaust valve opens and the exhaust starts to flow out. As the piston continues its downward stroke, it uncovers the inlet ring and allows fresh air to enter. This scavenging air has a straight run from bottom to top of the cylinder and firmly pushes the burnt gases out. A very high efficiency is obtained with this type of scavenging. Employed, for example, in this 6-cylinder, 150 horsepower engine made for heavy transport work. The cylinder liners have just one ring of ports for the inlet and 2 parallel valves for the exhaust in the cylinder head. But the 2-stroke engine generally, and proudly, claims to have done away with valve gear. Can one get the efficiency of end-to-end scavenging, but without the valve? Well, one solution is, instead of an extra valve, have an extra piston. Start with the normal end-to-end scavenged diesel. Lose the valve, double the stroke of the cylinder, make the exhaust duct into an exhaust ring, make that end of the cylinder exactly the same as the other, put the fuel injector in the middle, and finally add the second piston. So we get the opposed piston engine. 2 pistons in one cylinder which move towards and away from the center where the fuel is injected. Now, by careful arrangement of the couplings, the piston at the exhaust side leads and uncovers the exhaust ring first, so that the usual blowdown occurs before the inlet is opened a moment later by the second piston, when the scavenging air enters in such a way that it clears the exhaust ports just before the first piston closes them again. And we have end-to-end scavenging without a valve. Several modern engines are based on this principle. These cylinder liners are for a 90 horsepower heavy transport engine. At one end, the inlet ring, at the other end, the exhaust ring. Pistons are inserted at opposite ends of the liner. But in combining the output of the opposed pistons, some complications return. Gears may be used, but this engine employs levers. The pistons work backwards and forwards in the same cylinder. They drive the rocker arms, which at their other ends are attached to a common crankshaft, here seen in a mirror under the engine. The driving force in vehicles like this lorry. So in all these two-strokes, whether diesel or petrol, the gases themselves in scavenging are doing a lot of the work done by the piston in a four-stroke engine. And scavenging can be made even better by the careful shaping of the inlet and exhaust systems so that over a certain speed range, we get resonance. That is, the pressure wave caused by each explosion is reflected back along the pipe at just the right moment to help suck the old gas out and the new gas in. This produces a sharp increase in power, and racing drivers speak of feeling the megaphone come in. A large marine diesel turns over much more slowly, probably a maximum of about 120 revolutions a minute. And here, the exhaust gases are still made to do work, but in a different way. When they emerge from the cylinder, the energy still in them is used to drive the turbo blowers. These compress fresh air, which is then fed back to the inlet ports. So again, by careful application of the gas flow, we practically get something for nothing. The engine is now undergoing its final tests before acceptance by the owners and the underwriters. Tests which take a full 24 hours and will give a final answer to years of research and months of construction. Constant full load, half load, reversing. Tests on each individual cylinder. The 6 cylinders which combined give an output of nearly 8,000 horsepower. Over the last quarter century, improvements in scavenging and the addition of turbo blowing have practically doubled the output of this kind of engine. Now for the final tests, maneuvering. Backwards and forwards, the giant engine is thrown to see how many times it can be stopped and restarted on one tankful of air. A vital need when a ship is working its way into harbor. Traversing is particularly simple with a valveless two-stroke engine. Now forward again, after that backward. The starting air pressure falls, little by little. Nearly zero, but more than enough maneuvers. The engine's okay, passed. The order is full speed ahead. Into perhaps a ship like this, the largest two-stroke afloat. 45,000 horsepower from 3 engines. 3 horsepower from one engine, but also a two-stroke. Symbol of the increasing number of small two-strokes, which because of their simple construction are cheap to produce and cheap to maintain. A new and growing force in the world of everyday travel.